So Anna, team, fire away.
Thank you, Mr. Fever. Okay. Hi, I'm Anna.
I'm Audrey.
I'm Monik.
I'm Jace.
And this is our presentation, the Phantom Power Pauser. So the problem is phantom power, or standby power, which is the electricity that your appliances take when plugged in but not turned on. This means that any appliance that is currently plugged into an outlet is consuming electricity, even when it might seem like it's off. With more than 14 million homes in California and 134 million in the nation, these small numbers stack up quickly, with more than just a TV on in each home, resulting in about 3.9 trillion kilowatt hours consumed per year. But what does this mean for the consumer? Having just one TV alone on standby can be more costly than one anticipates, with just an average TV running for 1 hour per day in the year, adding up to $247 a year. That's just one TV.
And so from an analysis on energy trends since COVID-19, Sense.com found that electrical usage increased 22% since 2019, and PR Newswire found that 5 to 10% of that comes from standby power. Given that our average San Diego household spends around $95 to $130 monthly, you could be saving anywhere from $57 to $156 annually, and this does not even account for devices that are currently powered on.
Moving into our market research, we thought this product would be useful for everyone home using appliances more often. And this is especially true during a pandemic when people are more likely to leave things on since they're using appliances more often. Although this is aimed at every appliance owner in North America, with higher electricity rates in California, paying bills can turn out to be more expensive than other states, so it can turn out to be a bigger benefit for them.
And to get a feel for the market, we decided to go into looking at prior products and patents. So the first one you'll see on the screen is the energy monitoring system. And similar to its namesake, it just monitors the energy instead of, but we didn't want that, so we wanted to save our energy. And it also needs to be professionally installed, which would cause more inconvenience, where we wanted ours to be more user-friendly. And our second product that we'll see on the screen is the air conditioning unit. And also similar to its namesake, it's a more energy efficient solution to the cooling system. And it is only targeted towards the air conditioning unit, whereas we wanted our product to be more versatile. And the last product that we'll show you is the Casa Smart Plug, which most closely resembles our product because it is a smart outlet that connects appliances using Wi-Fi. It can turn off devices, and it can also set timers from an app, but it could be a hassle with unstable Wi-Fi, and also not everybody carries their phone around with them at all times in the house. And also the user needs to manually turn it on and off still, but we wanted ours to be more hands-free.
Okay, moving into our initial ideas. Our first involved several smart plugs connected through a single mounted controller, similar to a thermostat. And so all of these smart plugs would be connected to that thermostat. And so the user could use that to set timers and view power usage and then turn those plugs off or on. But we decided against it because we thought it would be inconvenient for regular use. If the user would want to turn off an appliance in one room, they would have to walk around into the room with that central controller in order to switch it on or off. And so to combat this, we could potentially have created an app to control those outlets and plugs. However, we decided against it because it would create another layer of complexity in this project. And so our second idea was a proximity tracker that the user could either store into their pocket or clip onto themselves. And so it would essentially cut power if the user were to leave their home or a certain area and doesn't require any manual input. However, we decided against this idea too because the user may not always have that tracker on them, where they could potentially lose it, and it would be difficult to use in households with multiple people.
Our final design is a combination of all those ideas. Instead of a proximity tracker, we would use a motion sensor to sense motion in front of the sensor, which would turn on the appliance. And after a set amount of time of no motion is detected, then it would cut power to appliance. And we wanted this to be controlled by an Arduino, so we could record power usage and also set a timer after no motion is detected.
Moving into our design specifications. Our first was that it had to disconnect power to the appliance. This was a disqualifying design requirement because if we didn't disconnect the power, phantom power would still be drawn and the problem is not solved. Our second was that it had to plug into a US Type E outlet. This was because people can't use the product if they can't power it and plug it in, and we chose this type of outlet since it's the most common outlet in North America, and we wanted the most people to be able to use it and have access. Our third disqualifying requirement was that our device has to hold a constant 120 volt AC connection. This was because our device needs to sustain the voltage and amperage that is coming from the outlet that was mentioned in the previous slide, and we want to make sure that it can plug into any home safely without any issues. Our fourth and final disqualifying design requirement was that it has to consume less power than the appliance. So simply put, if the design takes more power than the appliance that's plugged into it, you're not saving power. And our goal is to save money for the consumers by cutting power that they're not using instead of adding on to it.
And our fifth design requirement was that it needs to connect to a central control unit, because we found that this was a common feature in other products just because of the convenience. And this also piggybacked off of a thermostat idea, so everything would be in one centralized location. And our sixth design specification was that it cannot cover adjacent wall outlets, because after looking through reviews of online products such as the Casa plug, consumers generally preferred to have more outlets free. And our last design specification was measuring power consumption and relaying that to the user, because consumers wanted to know how much they're saving, and so when they see on an LCD screen that when wattage is 0, they would know that power is cut.
Moving on to designing and planning, we had to create a parts list. So these are our parts. We have an Arduino Mega 2560, Arduino power supply, a Mega breadboard shield, an AC line module, an LCD display, a PIR sensor, an SPST relay, current sensor, and a wall outlet. And with these parts, we created a block diagram, which basically shows us a rough layout of our connected components. And there are two parts in this block diagram: our Arduino, which is connected to our IR sensor, relay, and current sensor, and then our 120 volt line, which connects our wall outlet to the relay and then to our appliance. Using this block diagram, we created a circuit schematic, which is similar to the block diagram, but it shows our correct pins that we're going to connect to the Arduino. And to measure power consumption, we would need a voltage. We would need to find voltage and current. We can measure current using our current sensor, and we can use the onboard Arduino voltage sensor, but we would need to meet its spec, which is 5 volts maximum. So to calculate the resistance needed for our voltage divider, we needed to substitute Kirchhoff's voltage law into Ohm's law and then solve for resistance needed. We also needed to add a diode to clip that negative voltage, because our analog to digital converter on our Arduino is not rated for negative voltage.
And moving on to our state diagram, this diagram just generally maps out how our device should function logically. And so we have 3 states that it switches between: the reset state, the no human present state, and the human present state. And so going into the reset state, every time the reset state is entered, our PIR sensor should calibrate for approximately 1 minute. And so if the reset button on the Arduino is pressed, or it is manually powered off and on, then it will go through the reset state again. And so once it enters the no present state after the reset state, the relay will be open by default, meaning your appliance should be off. And so in this state, it checks for a minimum amount of motion over a certain time interval. And so if it does not meet that minimum amount of motion, it will continue to cycle through the state until it does reach that condition. And so once it does reach that condition, it will transition into the human present state. And so once our device now enters this state, the relay will be set to high, meaning your appliance should be on and running. And so it runs a similar loop where it checks for a minimum amount of motion over a certain amount of time. However, in this state, the minimum amount is higher, and it is over a longer time interval. And that longer time interval is to essentially give the user a set of buffer time, just in case they need to step out for a small moment to take a call or get water or something of the sort. And so if it does meet that condition within this loop, then your device will stay on and continue running for however long that condition is true. And so once that condition is false, it will return to the no human present state and continue checking.
So here's a demonstration of what our device looks like in action. It turns on when a person is in range after a counted cycle, and it turns off when the person is out of range and the timer is over. As you can see, when the hand is out of view, the light turns off and to represent the appliance. And in this video, the times are shortened for presentation purposes. But in the case of a television, the device would be off when the person is not in the room, but as soon as the person walks in, it acts like a normal television in standby mode. So the person would use a TV, would use a remote on the TV like a normal remote. And since very little motion is needed, they can sit back and relax. But as soon as the person exits the room, the device turns off after 5 minutes, saving the power. Here is a original sketch of the case that we had in the first demonstration. So our original had the LCD and the outlet on top and our IR sensor in the front. And our second design had the LCD in front for ease of view and the outlet in the back. For our actual design, we made it out of cardboard and we eliminated the LCD, and we'll explain why later on. But here's our first prototype out of cardboard. Based on this design, a final version was created out of foam board, and it has 3 layers of foam on the bottom with cutouts in the top 2 to hold each component in place, as well as the outlet and line module screwed in. This allows us to open it all the way and have Velcro on the top 2 corners to hold everything in place.
Moving on to design specs and testing. To test adjacent outlets and a Type B outlet, our design should be able to plug into a US Type B wallet and also not cover up adjacent wallets. So in that video, our design allowed the outlet above and below of it to be available. And for a central control unit, our Arduino should be able to control all the components, and it should follow the state diagram without deviation. And if it deviated from that state diagram, this would fail our design spec. To stop power, our relay needs to stay open or stay closed when to open or close the circuit. And we tested it by having our Arduino open and close the relay. And if it did that, then it passed.
And so to sustain 120 volts, this video just shows a time lapse of our device running for 2.5 hours while our connected appliance is running. And so we chose to run it for that duration because the average time a person watches their television is 2.5 hours according to the US Bureau of Labor Statistics. And so for power consumption, we measured the voltage and current of our device while the relay is closed, as seen in the first picture, and while it is open, as seen in the second picture, using a multimeter. And so we found the power consumption of our device to be 1 watt while the relay is closed and 1.9 watts while it is open. And so we took that value and compared it to several PlayStation 4 and PlayStation 4 Pro models. And as seen in the table, compared to our device while running, these several models, the power consumption of these models while at rest is significantly higher compared to the power consumption of our device while it is running. And so our device overall consumes a decent amount less power overall.
The only design spec we did not meet was being able to measure our power consumption. We did not pass because we did not use the LCD voltage divider and current sensor. This design spec only provides the user with information, so it doesn't really hinder the main goal of our design, which is to cut power or power a connected appliance.
And so in a survey of 25 people, with 6 of them being industry professionals, stakeholders were asked to provide feedback through a Google form on our project, as well as any other comments they had for possible future iterations. And so one of our stakeholders that we're about to feature is Mr. Ng, who was concerned about the motion sensor being our only trigger and also suggested that we should create more conditions to be met just in case our device would be triggered unnecessarily. And our second stakeholder is Mr. Laubach, who suggested that our motion sensor could be wirelessly connected so that we can set different positions without worrying about the wiring or where our device is, that it could still reach its full range. And additionally, he also brought up the fact that this product would save money even when the appliance is powered on, because it would turn off an appliance that would usually be left on for longer, effectively lessening the amount of power that it draws.
Here's some future changes we would like to see in our device if we were to continue it. So we started with the bare minimum as a foundation to build upon and add more features. One of these features would include an LCD. This would allow us to display the current and the voltage, as well as more settings for the user with a rotary encoder. And in these settings, the user could control the timers, the sensitivity of the IR sensor, and the delay after no motion is detected. In terms of cleaning and downsizing, we would like to have better wire management, a more portable case, and a smaller Arduino, since the one we have currently overcompensated our processing power. For reliability, we would like to have better cooling and airflow to make sure we preserve the longevity of our components.
And finally, we'd like to thank our mentors and teachers, our industry professional stakeholders, and our general public stakeholders for helping in the completion of our product.
Fernando here. Thank you so much for your presentation. It's very thorough. I really enjoyed that you guys have really looked upon all aspects of the design and possible areas where it could be improved. You mentioned that your product could be centralized. Is there any limit in terms of the number of power outlets that you could have in a home?
Well, currently we have an outlet in the back of our product. So that one only accounts for, I think, 2 outlets. But in future iterations, we can make it something like a power strip, and that would also just help our product a little bit more.
I only asked that question because there are a lot of short range communications, especially as the smart homes go, and you have a centralized thermostat and so forth. Depending on the number of appliances or outlets and so forth, that there could be a limit in terms of the number of outlets that you could have that you want to basically monitor and so forth. So it basically depending on what your communication link is, whether if it's Bluetooth, as you know, you guys are very well versatile in your mobile devices. So if you connect this to a sound bar or something, there are a number of limits in terms of number of devices that you could connect to that. So depending on whether you use wireless other means, there could also be a limitation. So that was the only reason why I was asking to see if you guys looked into that problem as well. So that was just a question around that.
I've got a question. Well, actually, 2 questions. I had some connection problems and I missed a portion at the beginning there. But what was your target cost for this device? And what do you think that you would be able to manufacture it for if you were to try to develop this?
So our target cost would generally depend on, I guess, like how much we would say it is, but well, sorry, it is like we didn't exactly think upon the cost of this, but rather how many people it would affect and like how it would just generally affect our consumers. And yeah. Okay,
so I'm just kind of looking at this. I suspect, based on the numbers that you put forward for the cost that's being used per TV per year, you could probably make it an attractive price. But the only reason that somebody would buy this, of course, would be to save money. Mm-hmm. I mean, maybe you can find a few good-hearted people that are trying to save energy, but so it would be from the standpoint of it really being able to take off. It would have to be something that would pay back in a reasonable amount of time. So it would be good to highlight that if you say I could manufacture and sell this for $100 and I'm going to save $200 a year, I get paid back in 6 months, and that's a pretty good deal. So that's just one suggestion. And I have a question. Do you have any idea why your system uses more power when it's off than when it's on?
Our device uses more power when it's on than it's off, because when we say open and close, that means like when our relay is closed, so power is going through. So that would cause more.
Okay.
Yeah.
Let's say I mixed that up. Thank you. Thanks for the clarification.
All right, thank you very much. Great job, you guys. And we're going to go on to our next ones, which is Kat, Jonah, and Eli. Kat, Jonah, Eli, you guys ready to go?
Yeah, let me share.
Yeah, we're ready.
All right. Whenever you guys are ready.